Welcome to all in the lecture series of functional analysis. Now in this lecture we see very important lemma, that is the lemma 2.4.1. This lemma is very important because we use this lemma to prove the many properties of finite dimensional non-linear space. So the statement of this lemma is, let x1, x2 up to n xn be a linearly independent set of vectors in a norm space capital X, where capital X is of any dimension. Then here we have to show that there is a number c greater than 0 such that for every choice of scalars alpha 1, alpha 2 up to n alpha n, we have the inequality, that is norm of alpha 1 x1 plus alpha 2 x2 up to n plus alpha n xn, that is greater than or equals to, we write S is equals to mod of alpha 1 plus mod of alpha 2 up to n plus mod of alpha n. Then equation 1 can be written as norm of alpha 1 x1 plus alpha 2 x2 up to n plus alpha n xn, that is greater than or equals to c into s. That means our equation 1 become now norm of alpha 1 x1 plus alpha 2 x2 up to n plus alpha n xn, that is greater than or equals to c into s. Now here s, that is equals to mod of alpha 1 plus mod of alpha 2 up to n plus mod of alpha n. For this s, we consider the two cases. In case 1, we consider s equals to 0, and for this s equals to 0, we have to prove this inequality 2. Another case we consider, that is the case 2, in that we consider s that is not equals to 0, and in this case also we have to prove the equation 2. In this way we prove this lemma. Now case 1, here we consider s equals to 0. If s is equals to 0, then putting the value of s, we get mod of alpha 1 plus mod of alpha 2 up to n plus mod of alpha n, that is equals to 0. That means thus implies that for all j is between 1 less than or equals to j less than or equals to n, mod of alpha j, that is equals to 0. That means the sum of non-negative term, it is equals to 0, implies that each term must be equals to 0, and therefore for each j, mod of alpha j, it is equals to 0. Now mod of alpha j, it is equals to 0, implies that alpha j equals to 0 for all j, and alpha j is equals to 0. It means that in equation 1 we get this s, that is also 0, and here alpha 1, alpha 2 and up to n alpha n, all these terms are 0. It means that this term, that means therefore in equation 2 we get that all the alpha j's are 0, implies that norm of alpha 1 x1 plus alpha 2 x2 up to n plus alpha n xn, that becomes 0 because all the alpha j's are 0, therefore this norm is 0. In the same way here, as the value of s, in our case 1 the value of s is 0, and therefore and cs, that is also equals to 0 because s equals to 0, and therefore these two terms are 0, implies that therefore here we get that this term is equals to 0 and that term is also equals to 0, and 0 is always greater than or equals to 0. Actually it is equals to 0, but we may write it as 0 greater than or equals to 0, and therefore equation 2, that is the equation 2 is true for s equals to 0, and therefore if s equals to 0, then equation 2 is true. Now we consider the case 2. Now here in case 2, we consider s that is not equals to 0. But as s equals to mod of alpha 1 plus mod of alpha 2 up to so n plus mod of alpha n, that is the sum of the absolute values. It is also sum of the non-negative terms, and always it is greater than or equals to 0. But here we are saying that s not equals to 0 implies that s is strictly greater than 0, and therefore s is strictly greater than 0, that means s not equals to 0. So we divide equation 2 by s. We get norm of alpha 1 x1 plus alpha 2 x2 up to so n plus alpha n xn. It is greater than or equals to c into s. This is the equation 2. Now we divide equation 2 by s. That means we divide this is by s, and here we also divide by s. Here this s get cancelled, and here as s which is strictly greater than 0, and therefore mod of s that is also strictly greater than 0, and therefore mod of s, it is again equals to s, and therefore here this is written as norm of alpha 1 by s into x1 plus alpha 2 by s into x2 up to so n plus alpha n by s into xn, that is greater than or equals to c. Because here as we are taking s greater than 0, and therefore mod of s that is also greater than 0, and therefore it is again mod of s equals to s, and therefore 1 divided by mod of s, that is also 1 divided by s. And for any norm of alpha x, we always know that it is equals to mod alpha into norm of x, and therefore here as we have here that norm of alpha 1 x1 plus alpha 2 x2 up to so n plus alpha n xn. Okay, and it is divided by s, and therefore it is equals to 1 divided by s into norm of alpha 1 x1 up to so n plus alpha n xn. Okay, and it is equals to 1 divided by mod s into again norm of alpha 1 x1 plus up to so n plus alpha n xn, and it is equals to, now as here we are saying that norm of alpha x that is equals to mod alpha into norm of x, it is equals to, here we are taking that instead of 1 by mod s, we may take it as mod of 1 by s into this, and now it is equals to, it becomes norm of 1 by s in bracket alpha 1 x1 up to so n plus alpha n xn. It is equals to norm of alpha 1 by s into x1 up to so n plus alpha n by s into xn. This is the simplified form, and hence we write down that norm of alpha 1 s into x1 plus alpha 2 by norm of alpha 1 by s into x1 plus alpha 2 by s into x2 up to so n plus alpha n by s into xn, that is greater than or equals to c. Now here for the value alpha 1 by s, we write down beta 1. That means here we write down this is norm of beta 1 x1 plus beta 2 x2 up to so n plus beta n xn it is greater than or equals to c, where for each j j is from 1 to up to so and n, we write down beta j equals to alpha j by s. But here then summation j is from 1 to n mod of beta j, that is equals to summation j is running from 1 to n, just putting the value of beta j. The value of beta j is mod of alpha j by s. Now here s is greater than 0, therefore it is equals to summation j is from 1 to n mod of alpha j divided by s, and that is equals to, now summation j is from 1 to n mod of alpha j, this is nothing but s divided by s, and that is equals to 1. Therefore here the summation j is from 1 to n mod of beta j, that is equals to 1. Thus here the equation 2 becomes, thus we can write norm of beta 1 x1 plus beta 2 x2 up to so n plus beta n xn, that is greater than or equals to c. Summation j is from 1 to n mod of beta j, it is equals to 1. We give it the equation number 3. Norm of beta 1 x1 plus beta 2 x2 up to so n plus beta n xn greater than or equals to c, with summation j is from 1 to n mod of beta j equals to 1. That means our equation 1 now reduced to this form of equation 3, and therefore hence it is sufficient to prove the existence of c, greater than 0, such that equation 3 holds for every n tuples of scalars. Equation 3 holds for every n tuple of scalars beta 1, beta 2 up to so and beta n, with summation j is from 1 to n mod of beta j equals to 1. And we have to prove the existence of c greater than 0 such that equation 3 holds for every n tuples of scalars, with summation j is from 1 to n mod of beta j equals to 1. That is here we have to prove. Now to prove this, here we use the method of contradiction, and therefore in the method of contradiction we assume that this is not true. That means there does not exist any c satisfying 3. That means here for every c greater than 0, that means we are taking the negation of this statement, and the negation of this statement becomes for every c greater than 0, there exists, here we are saying that for every n tuples of scalars, and therefore here in negation it becomes there exist n tuple of scalars beta 1, beta 2 up to so and beta n, beta 1, beta 2 up to so and beta n, with summation j is from 1 to n mod of beta j equals to 1, and norm of beta 1 x1 plus beta 2 x2 up to so n plus beta n xn, that is lesser than c. That is our assumption. This is our assume. We assume that for every c greater than 0, there exists n tuple of scalars beta 1, beta 2 up to so n beta n, with summation mod of beta j equals to 1, but norm of beta 1 x1 plus beta 2 x2 up to so n plus beta n xn, that is less than c. Now here we say that it is true for every c greater than 0, and therefore we are taking the value of c. So firstly we take therefore for c equals to 1, which is greater than 0, there exists n tuple of scalar. There exists n tuple of scalars. Now we give it the name beta 1 1 comma beta 2 1 up to so and beta n 1 with summation j is from 1 to n mod of beta j1 equals to 1 and norm of beta 1 1 x1 plus beta 2 1 x2 up to so on plus beta n1 xn, that is less than 1. Now again for we are taking the value of c is now it is equals to half. It is again greater than 0, and therefore for this value there exists n tuple of scalars. We give it the name beta 1 2 comma beta 2 2 up to so and beta n2 with here we are writing summation j is from 1 to n mod of beta j2, it is equals to 1 and norm of beta 1 2 x1 plus beta 2 2 x2 up to so n plus beta n2 xn, that is lesser than 1 by 2. Now here for this linear combination beta 1 1 x1 plus beta 2 1 x2 up to so and beta n1 xn, we give it the name it is equals to norm of y1. That means here norm of y1 equals to this, that is lesser than 1. In the same way for this we give it the name norm of y2, that is equals to norm of beta 1 2 x1 plus beta 2 2 x2 up to so n plus beta n2 xn, that is lesser than 1 by 2, and so on. We continue these steps. Therefore for c equals to 1 by m, that is greater than 0, again there exists n tuple of scalar. There exists n tuple of scalars beta 1m comma beta 2m up to so and beta nm with norm of ym, that is equals to summation beta 1m x1 plus beta 2m x2 up to so and beta nm xn, that is less than 1 by m. With here again about the scalars we have summation j is from 1 to n mod of beta jm, that is equals to 1. Now here and this process is continue. Now here as we get here that norm of ym, that is equals to norm of beta 1m x1 plus beta 2m x2 up to so n plus beta nm xn. Now this is lesser than 1 by m, and as it is less than 1 by m and this is continue, therefore as m goes to infinity 1 by m goes to 0. 1 by m goes to 0, it means that norm of ym, that is lesser than 1 by m, that goes to 0 as m goes to infinity. It implies that the sequence ym, the sequence ym is a convergent sequence and it converges to 0. We give it the equation number 4. This implies that sequence ym converge to 0. Now here we get that summation j is from 1 to n mod of beta jm for each m. Summation j is from 1 to n mod of beta jm, that is equals to 1, and therefore for each fixed j, for each fix j mod of beta jm, which is always less than or equals to summation j is from 1 to n mod of beta jm, and that is equals to 1. That means for each fixed j, for each fixed j mod of beta jm, it is less than or equals to 1. It means that is for each fixed j, for each fixed j sequence beta jm is a bounded sequence, because all the terms of the sequence are less than or equals to 1. Because here all the terms of the sequence, because in the sequence beta jm the terms are like this, here j is fixed, therefore all the terms of the sequence are like this: beta j1 comma second term is beta j2 comma and so on, the mth term is beta jm and so on. Here we observe that all the terms are less than or equals to 1, and therefore for each fixed j the sequence beta jm is a bounded sequence. Now as it is a bounded sequence, and therefore here we apply the Bolzano-Weierstrass theorem, and that theorem says that Bolzano-Weierstrass theorem, that theorem is that every bounded sequence, every bounded sequence has limit point. Every bounded sequence has limit point. As every bounded sequence has limit point, it means that there exists a subsequence which converges to that limit point, and therefore this sequence has a subsequence which converges to that limit point, and therefore here now we are taking j equals to 1, therefore for j equals to 1 the sequence beta 1m is a bounded sequence, and therefore by Bolzano-Weierstrass theorem this sequence has a convergent subsequence. Therefore by Bolzano-Weierstrass theorem sequence beta 1m has a convergent subsequence. Say gamma 1m, that is the subsequence gamma 1m, it converges to, we are taking that limit as beta 1. That means here gamma 1m converges to beta 1 as m goes to infinity. I repeat the process again. As here we get for j equals to 1 the sequence beta 1m, which is a bounded sequence, and by Bolzano-Weierstrass theorem this sequence has a subsequence gamma 1m such that gamma 1m converges to beta 1 as m goes to infinity, and therefore as ym that is equals to beta 1m x1 plus beta 2m x2 up to so on plus beta nm xn. And here beta 1m has a subsequence gamma 1m x1 plus, here all the scalars remain as it is, beta 2m x2 up to so on plus beta nm xn. Now here we give it the name y1m. Therefore here as the sequence ym in which ym equals to this, now this sequence ym has a subsequence y1m such that y1m equals to gamma 1m x1 plus beta 2m x2 up to so on plus beta nm xn. Now here we take for j equals to 2. For j equals to 2, again here the sequence beta 2m that is this sequence beta 2m, it is again a bounded sequence, therefore by Bolzano-Weierstrass theorem is a bounded sequence, therefore by Bolzano-Weierstrass theorem this sequence has a convergent subsequence, sequence beta 2m has a convergent subsequence, say we give it the name gamma 2m such that gamma 2m converges to beta 2, then we get, then corresponding all these terms, all these scalars we write down y2m that is equals to, now the first term is, the first scalar is gamma 1m x1 plus, now instead of beta 2m we write down here gamma 2m x2 up to so on plus, here all the scalars remain as it is beta nm xn. And therefore here we get the sequence y2m, now the sequence y2m is a subsequence of the sequence y1m, and y1m is a subsequence of the sequence ym. And in this way, as here we start with j equals to 1, we are getting this bounded sequence having the convergent subsequence gamma 1m converging to beta 1, and then here corresponding to that, here we get the subsequence y1m which is a subsequence of the sequence ym. In the same way for j equals to 2, we again getting the bounded sequence beta 2m, this is a bounded sequence is this, and this bounded sequence, again this bounded sequence has a convergent subsequence by Bolzano-Weierstrass theorem, say gamma 2m and gamma 2m that converge to beta 2, and therefore the corresponding we get the subsequence y2m. Now sequence y2m, it is a subsequence of the sequence y1m, and that is a subsequence of the sequence ym, and this process is continue after the nth term. Therefore for j equals to n, we get the sequence beta nm. Now beta nm is become again a bounded sequence because all the terms are less than or equals to 1, as we see is a bounded sequence. Now beta nm is a bounded sequence, therefore by Bolzano-Weierstrass theorem, sequence beta nm has a convergent subsequence, say gamma nm such that gamma nm converges to beta n as m goes to infinity, and therefore here we get therefore the corresponding ynm that becomes now the first term is now here gamma 1m x1, the second term is gamma 2m x2, the third term becomes gamma 3m x3, and so on. The last term become gamma nm xn, and therefore here we get the sequence y1m. Now it is a subsequence of the sequence yn minus 1m, and so on. Therefore here the sequence ynm, it becomes a subsequence of the sequence ym, because here we are getting the sequence y1m, that is a subsequence of the sequence ym. Sequence y2m, that becomes a subsequence of the sequence y1m, and that is a subsequence of the sequence ym, therefore it is also the subsequence of the sequence ym. In the same way, the sequence ynm becomes a subsequence of the sequence ym such that ynm equals to gamma 1m x1 plus gamma 2m x2 up to so n plus gamma nm xm. Now here we write down this ynm as it is ynm equals to summation j is from 1 to n gamma j m xg, where summation j is from 1 to n mod of gamma j m, that is equals to 1. Now here that is ynm, it is equals to summation j is from 1 to n gamma jm xj with summation j is from 1 to n mod of gamma jm, it is equals to 1. Here we write down that this sum equals to 1 because here we know that the sequence gamma jm, it is a subsequence of the sequence beta jm. It is a subsequence of the sequence beta jm, and for the sequence beta jm we have here summation j is running from 1 to n mod of beta jm. This sum is equals to 1, and it is a subsequence of the sequence beta jm, and therefore the summation j is from 1 to n mod of gamma jm, that is also equals to 1, and therefore we are write down this sum is equals to 1. Now here all the scalars gamma jm are like this. For each j gamma jm that converges to beta j as m goes to infinity. Here we observe that, and therefore ynm, that is equals to gamma gamma 1m x1 plus gamma 2m x2 up to so n plus gamma nm xn. Now here we observe that for each j beta gamma jm converges to beta j, and therefore here we say that gamma 1m that converges to beta 1, the gamma 2m that converges to beta 2 up to so n gamma nm that converges to beta n, and therefore this sum converges to beta 1 x1 plus beta 2 x2 up to so n plus beta n xn, and now we give it the name y when as m goes to infinity, that is ynm converges to y as m goes to infinity. Now here the y, that is equals to beta 1 x1 plus beta 2 x2 up to so n plus beta n xn. For each j, gamma jm converges to beta j as m goes to infinity. That means gamma jm that converges to beta j as m goes to infinity, and therefore mod of this that converges to mod of beta j for each j. For each j, mod of gamma jm converges to mod of beta j, and therefore the summation j is from 1 to n mod of gamma jm, mod of gamma jm that converges to the summation j is from 1 to n mod of beta j, but it is equals to 1, and therefore summation j is from 1 to n mod of beta j that is also equals to 1. As summation j is from 1 to n beta j equals to 1 implies that not all beta j's can be 0. Since if for all j beta j equals to 0 implies that the summation of mod of beta j that is equals to 0, and here we get that summation of mod of beta j equals to 1, and therefore not all beta j's can be 0. As not all beta j's can be 0, and here we have to given that the set of all the vectors x1 x2 up to so and xn, it is a linearly independent set of vectors. As it is linearly independent set of vector and not all beta j's can be 0, therefore beta 1 x1 plus beta 2 x2 up to so n plus beta n xn, it is also not equals to 0, but this is nothing but that is y not equals to 0. On the other hand here we get that ynm that converges to y, and norm is a continuous function, therefore ynm converges to y implies that norm of ynm converges to norm of y as m goes to infinity. As sequence ynm is a subsequence of the sequence ym, and we get that norm of ym that is lesser than 1 by m, and that goes to 0 as m goes to infinity. That means here the sequence ym, it is a convergent sequence and it converges to 0, but the sequence is convergent and it converges to 0, therefore its every subsequence also converges to 0, and therefore it implies that sequence ynm that also converges to 0, but norm of ynm that converges to norm of y as m goes to infinity. That means here we get that norm of ynm converges to 0 as m goes to infinity, as well as norm of ynm that converges to norm of y as m goes to infinity, and we know that the limits are unique, and therefore it implies that norm of y it is equals to 0, but here we get that as norm of y equals to 0 implies that y equals to 0, and here we get that y is not equals to 0. These two gives, if we give it the equation number a and we give it the equation number b, then from equation a and b we get the contradiction. From equation a and b we get contradiction. we get contradiction. And therefore, our assumption, what is our assumption? Our assumption is that for every c greater than 0, there exists n tuple of scalar, there exists n tuple of scalars beta 1, beta 2 up to so and beta n with summation j is from 1 to n mod of beta j equals to 1 norm of beta 1 x1 plus beta 2 x2 up to so and plus beta n xn, that is less than c, is wrong. This is our assumption. It becomes wrong because it gives us a contradiction, and thus it says there is a c greater than 0 such that for every choice of scalar there is c greater than 0 such that for every choice of scalar beta 1, beta 2 up to so and beta n with summation j is from 1 to n mod of beta j equals to 1 norm of beta 1 x1 plus beta 2 x2 up to so and plus beta n xn, that is greater than or equals to c. This is the proof of the lemma.